We're going to compare gravitational fields and electric fields. Firstly, gravity acts on objects with mass, while electric field acts on objects with charge. And gravity is always attractive, while electric fields can be attractive or repulsive. So if it's unlike charges like positive and negative, then it would attract, while if it's like charge like positive and positive and negative and negative, it would repel. The definition of gravitational field strength is force per unit mass on a test mass, while the definition of electric field strength is force per unit charge on a test positive charge. So two major differences there. One, electric field strength is per unit charge instead of per unit mass. And secondly, electric field strength is a bit more specific about the direction. It's on a test positive charge. It needs to be this specific because electric fields can be attractive or repulsive. They can both have uniform fields like so. So in the first example, gravitational field strength can be uniform when it's close over small distances, for example, on the surface of planets. And by small distances here, we're talking about a couple of kilometers at least. While in the electric field strength, the uniform field is, for example, between two parallel plates. Now, if I put a test mass here, it would be attracted in the direction of the gravitational field lines. While with the electric field, if I put a test positive charge, then it would be attracted in the direction of the electric field lines. But if I put a negative charge, it'd be in the opposite direction. So some slight differences there. We have radial fields in both gravitational fields and electric fields. But in electric fields, you can have the radial fields pointing away or towards it based on what type of charge it is. You can find the force on a mass in a gravitational field by using Newton's law of gravitation, like so. But in the electric fields, you'd use Coulomb's law, like so here. And you can see you've got masses for the first one and in Newton's law of gravitation, while for Coulomb's law, you've got charges. You can find the electric field strength and the gravitational field strength using these equations, which are derived from Newton's law of gravitation and Coulomb's law by dividing it by per unit mass in the first case, while in the second case, the Coulomb's law, you divide it by per unit charge, so you divide it by charge there. Another similarity between these laws is that they both follow the inverse square law because you got r divided by r squared at the bottom of all of those equations. So if you double your distance, the force for either both of them would become a quarter. Okay, constant proportionality in the first one is g, while the constant proportionality in the second one there is 1 over 4 pi epsilon naught squared, where epsilon naught is the permittivity of free space. Okay, gravitational force is significant when considering large objects like with little overall charge, for example, planets and stars and so on. While electric field strength, that's the electric force there is a bit more significant and needs to be considered when you are dealing with less massive objects, for example, particles and droplets and so on, because it's unlikely large objects have an overall charge. Let me give you an example. In this example, I'm going to show the ratio of the electrostatic force to gravitational force between two identical charged objects is given by this equation here, where Q is the charged object, M is the mass object, G is the gravitational constant, and epsilon naught is the permittivity of free space. So let's start off with the force between these two objects, which is a gravitational force by Coulomb's from Newton's law of gravitation, and then you've got Coulomb's law for the electric force there. Now, because they're identical masses, capital M times lowercase m is m times m with the same m, so it's m squared. So I'm going to write it like this, and then and they have the same charge as well, so I'm going to instead of write q times q, I'm going to write as q squared. Okay, now I'm going to divide the electric force by the gravitational force because that's what the ratio is asking for. So if I do that, I'm dividing a fraction by a fraction. So take the bottom one, flip it over and multiply. Okay, so I've flipped over the Newton's law of gravitation and I'm multiplying it. Okay, so r squared from the top and bottom will cancel out. So actually, the ratio of the forces does not depend on the distance between those two objects. Okay, and that gives us the expression that we're looking for. Okay, part B, I'm going to determine this ratio between two protons. Okay, let's start off with that equation we just derived right now. And Q for two protons is 1.6 times 10 to the power minus 19. That's squared, 4 pi epsilon naught. Those are all constants we can get from our equation sheets. And then times mass squared. So that's the mass of a proton squared. And that gives us a number of 1.24 times 10 to the power of 36, which is a very large number. That shows us that the electrostatic force between two protons is much bigger than a gravitational force of attraction. So this is why when we're considering forces between protons, we ignore gravity because it's just not significant compared to the electrostatic force. Okay, part C, determine the same ratio but between two planets and the mass with a mass of the order 10 to 24 kilograms, and we're going to assume that each planet has a charge of around 1 coulombs. Okay, so this is just an approximation because overall a planet's charge should be fairly neutral. Okay, so let's put these numbers in. So for charge, we're going to put 1 coulomb, which is actually quite a lot, but in the grand scheme of things, I think we're going to find that it's not that much. 4 pi epsilon naught, they're all constants, and for mass, I'm using this order here, 10 to the power of 24, and I'm making sure that's being squared there. So that gives us a number of 1.3 times 10 to the power of minus 28, which is a very small number. This shows us that the electrostatic force between two planets is negligible compared to the gravitational force of attraction between them. This is why when we're considering force between planets and stars and so on, we tend to ignore the electrostatic force and we just consider gravity. Okay, finally, let's compare electric potential. Okay, so they're both, if you draw the equipotential patterns around a planet or a charge, they look very similar, like these concentric circles. They're actually surfaces because it's a three-dimensional objects here, but we can draw them on a diagram like so. You can determine the gravitational potential at any point from where r is the distance from center of the object using these equations here, and there's an equivalent in electric potential as well. And then if you want to find the gravitational potential energy, you just have to multiply by mass, while with electric potential energy, you would multiply the potential by the charge, like so. You can see that these equations look similar. There's another similarity here is the definition of potential. So it's at infinity, the potential is defined as 0. Okay, another similarity is you can see they're inversely proportional to distance from the center. That's why there's a 1 over r at the bottom of each of those there. However, with gravitational fields, you have a negative potential, always negative around it. So it would have, for example, minus 50 megajoules per kilogram. While with electric fields, it can be negative or positive, the potential around it. So around positive charge, the potential is positive because you would have to do work to bring another test positive charge closer to it. While with the negative charge, you don't have to do work to bring a test positive charge closer to it. It would be attracted and energy would release. So you've got a negative potential around it.